Let's get started. The purpose of the subject is the first thing we're going to talk about, and then I'm going to talk about this beta architecture and try to introduce you to what a processor architecture is like and how, in particular, this beta, which is this thing that we're going to use, works. So first, for the purpose of the subject, this is my little boy, Max, when he was 2 years old. Now he's 3. Basically, the purpose, I think, is fairly self-evident. What's going on behind the screen? Okay. Many of you, of course, all of you have taken the Structured Interpretation of Computer Programs class, and so you know how to program in software, but there's still this mystery, this black box of what actually is executing the code and how it actually gets turned into the results on the screen. It's also true, of course, for that thing in the back there that's doing whatever it's doing. So what sort of course material do you have? The lectures that I'm going to be given are actually not based on a textbook. Perhaps someday there will be a textbook based on this stuff, but right now the lecture notes themselves are actually the main text. And given how busy things are, I have the lecture notes from last term, from the last term that I taught it, that you can look at, certainly at MIT. But I'm also going to be trying to keep ahead 1 or 2 lectures over here in the website here, and so you can look at that set of lecture notes kind of as a text. There's also an additional textbook which is incredibly good by Hennessy and Patterson, and that will not follow along in any way, but it's really fun whenever you're dealing with a topic in class here to sort of look up the corresponding topic in the textbook there and see how they talk about it. So if you're looking for things to do, that's a very good book to look at, and you all have it. Besides just the lecture notes themselves, we're also going to make available on the website various reference material. And in particular, since we're going to be programming this kind of processor called the beta, there's going to be a set of references having to do with that. And you can see 3 of them right there. 2 sort of different ways to think about doing it. One was the recursive way, which is on the left. And you have, fact of n. If n is zipped, then you give back 1. Otherwise, you recursively call yourself with n minus 1, and then after you've recursively called yourself, you take the answer, multiply it by n, and keep on going. And then I believe you also learned about the iterative way to do it. And in Scheme, it's sort of a implied iteration, which is that here's fact iter, and as you recall, there was the input n here, and there was an accumulation variable called val, and if n was 0 in the base case, you brought back val, and otherwise you did the computation in the arguments before you called fact iter, and as a result of there being no work left to do after this call was made, this was thought of as a go-to to just go back here. In other words, this was just an iterative loop, right? And so what was nice about that, if you recall, is that you didn't need a stack. You didn't need to remember old stuff. You just had to spin around and around. So today we'll start out with the simple case, which is fact iter, and we'll talk about how something like this might be implemented in the instruction set of a processor. And in particular, we're going to start by looking at the processor, which I believe you did at the end of the Scheme book, right? And then we'll see how that particular instruction set architecture is a little different than the one that we're going to be doing here, which is called the beta. But hopefully that'll be a link to where we're going to go. So let's take a look at what hopefully you guys have seen before. And again, please let me know if you haven't seen this, because otherwise, I'll slow down if you haven't seen it. Okay. So here's fact iter, and if you remember from the sort of last few chapters of the book, there was this idea that you can implement this function not necessarily in the language Scheme, but in a language that is more primitive. And the one that they showed in the book was called the register machine language. And it had instructions that were like test and branch and assign and go to. And from all the nods, I guess you've all done this, right? Great. So how is it that this actually works? Well, first of all, since it's an iteration, we have a label for where the loop is going to be. And that label points right here, and that says, here's where the loop starts. And of course, at the end of the loop, we go to the label that's up here. And so what that says is when you get down here, change the program counter, which keeps track of where you are as you step through and count through the instructions of the program, and change it to go back to here. So you just keep going around and around. And inside of the loop itself, what do? Well, we're going to first test if n, which is in a register, is equal to the constant 0. And where did the result of this go? Anybody remember where the result of the test went? So we say test if n is equal to 0. And where do you store the answer? It doesn't say here, does it? So what was implied in the scheme textbook at the end there was that there was a condition register in which the results of all tests got stored, either true or false. And after you put something in the condition register, which is implied here, then you can decide whether or not to branch based on what's in there by calling the branch statement. And if the condition register was true, then the branch would be taken. Okay? So that was, and you probably did this very, very fast, right? So it's okay. But the linkage between these two lines isn't shown here. Okay? You have to know how the instruction set works in order to understand the linkage between the test and the branch. That off to the side there is a condition register which stores the result of the test, and then the branch is like an if statement which is executed only if the condition register has a true value in it. And so what that says is that if n is equal to 0, then this branch will be taken and we'll jump to the label done. And in this case we go to register continue. How many people remember what that was?
Stores the value of wherever we came from.
Wherever we came from. So if somebody called this as a subroutine, they do that by saying assign continue to where you want to come back. And then you say go to fact iter. Then this runs. And then at the end, you branch back. Okay? Go back to wherever you came from. So this is just a subroutine, branch back to whoever called us. Now, what's over here? If we don't take this branch, we do two assignments. The first one is we take the register val, multiply it by n, and put the result in val. So that's essentially saying val equals val times n, if you were to do it in C. And then over here, we take n, subtract 1 from it, and put the result back in n. And now val and n have been both updated to have new things in them, and then we jump back here. So this is a translation of this code into this type of code here. Okay, but this is a much more primitive code, which then later on in the scheme book was run on a computer that could execute and understand the instructions that were down there. Okay. Now, don't worry if you don't understand that code too well, because you're not going to need it, because we're going to do something different. Okay. But I wanted to show it to you, just kind of show you the linkage in between what you've already seen in the scheme book to what we're going to be doing here. And if for any reason that's fuzzy, what you may want to do is just go back to the scheme book. I don't think I have it here, but in the back of the purple book, and look up the register system and just kind of reread those pages to understand how that system worked. And then when we talk about the beta, you'll understand how the beta is different than that one. And it's only a little different, okay, but it is a very close link to that. Let's say we wanted to build a computer that could execute the register machine language of the SICP book. Well, what do we need to make this machine? Let's say that you were told that you need to build a thing. Well, first of all, you need memory. You need memory for two reasons. First of all, that program that I just showed you has to reside somewhere to get executed. Right? Somewhere there needs to be some storage inside the machine that remembers what the instructions are. And there needs to be a program counter that steps through them one at a time. Say, now it's time to do this, now it's time to do that, now it's time to do that, whoops, now it's time to branch back and go back into a loop over and over again. But there needs to be this memory. Okay? The second thing that we need is some sort of memory to store those intermediate values like val and n. And of course, if the program is more complex than fact, the amount of storage that you need is very, very big, right? If you want to write Microsoft Word, you need more than 3 or 4 words of storage. In fact, you need 64 megabytes of storage at least. Okay? So there's sort of two purposes to the memory. One is for instructions, the other is for data. The other thing that we would need to use to build a computer to execute that register machine language we just saw is some kind of a calculating device like a calculator in the old days with buttons, right? I don't, you know, and no one buys these anymore, but something that can add and subtract, do and or, you know, XOR, you know, stuff like that. And what this calculating device is called typically is a ALU, and that stands for an arithmetic/logic unit, because it can do both arithmetic operations like plus and minus and times, and logical operations like and, or, stuff like that. Okay? So besides these two things, which is sort of the hardware of what we need, we also need to sort of decide on certain things. We have to make certain design decisions about how the programs that are in the memory up here are going to be interpreted by the hardware. After all, a memory can only store bits of data. It cannot tell you intrinsically what those bits mean. Okay? It's when you read them and you say, oh, I know that this bit, if it's on, means something, or this bit when it's on means something else, that makes sense. So over here, we're going to have to decide on exactly what those instruction words look like, what those bits mean. And we're going to talk about two examples today. The first one, which I just showed you, is from the Scheme textbook and is the register machine language that's here. And we're actually not going to stay with that for very long. And the reason is that even though it is very elegant and simple and small, it's also not very practical. Okay, and we'll talk a little bit about why. But what we are going to do is we're going to shift very quickly from this example to one that's similar but not the same, called the beta. And the beta is actually based very loosely on the DEC Alpha, which some of you have heard of, right? And actually, I guess now it's made by Compaq, right, which owns DEC, or which bought DEC. And it's actually a really good architecture because it's what's called a RISC architecture. In other words, one of the most modern ones that are out there. And the Intel line, for instance, the 286, the 386, Pentium, etc., is actually a very old architecture that's been kind of goosed up more and more and more and more. And it's really not that great. And so we're not going to talk about that. We're going to talk about what they should have done many years ago, okay, which is to shift over to something which is much more like the beta. Now, once we decide on the meaning of the bits in the instructions, we now need a circuit which is going to look at those bits and control the calculator and the memory to actually execute what we want the instructions to do. When an instruction says add, the control logic will look at the bits of the instruction that we've decided stand for the code for add, and we'll press the add button on the hardware here and press the buttons on the memory to store the results where we want it to go. And what's incredible is that these four things are enough to build a system that we want. That's all that it takes. And that's, in fact, all that we're going to do for the next 3 weeks, is talk about basically those four things. The way that I lecture most of the time is I say things, and you kind of shake your head as to what the heck does he mean, and then I say it again, and then I say it again and again and again, and hopefully by the time, third or fourth or fifth time, it kind of sinks in what it is that I mean. So don't worry if when I first use a word, you don't know what it means, because you can be sure that I'll come back to it. The program counter I talked about, the thing that steps through the instructions one at a time, has to point into the memory to say, now it's time to do this instruction, now it's time to do the next one, now it's time to do the one after that. And so we will set aside a very small amount of memory by itself, which we will label the program counter. It will say where we are in the program right now, and the normal mode will be for that register, for that number of bits. It's actually going to be 32 bits long, okay, to increment and increment and increment and increment, and that will stand for stepping through the instructions of a program. When you do a goto, however, it will jump from where it used to be to some other place, not necessarily the one next door. It may jump back, it may jump forward, we're not sure. And if you have an if statement, it may branch one way or the other, either jump or not jump, depending on what the condition is that you're trying to test. So that's the second statement here. We need to have a way of not only having the program counter just bump forward all the time or unconditionally go back, but we're also going to have some logic to have the program counter's motion dependent on data values inside of the code. So if you think back to the factorial thing I just showed you there, it tested n to see if n was 0, and if it was, then it stopped, right? Then it said, I'm all done, base case, everything's finished. Okay, now we're talking about the PC here. What else did we need? Well, I showed you in the recursive example, or even, I'm sorry, in the non-recursive example, that at the end there was this idea of go to continue. In other words, go to the place where I was called, okay? Or right after the place where I was called is actually really what it is. We're going to need some way of dealing with that. And if you remember in the Scheme textbook, in addition to the continue register, you needed one other thing, which was a stack. And what the stack did is it allowed you to call a subroutine multiple times, or for one subroutine to call a different one, or for a subroutine to call itself over and over, which was for the recursive way of doing things. And we'll talk more about that on Sunday. But for now, we know that besides the memory to hold the instructions of the code, besides a memory to hold the data, besides a small amount of memory to hold the program counter itself, we're also going to need a stack somewhere, because we want to do subroutine calls and calls that call other things. And then finally, we have to figure out some way of managing all of this stuff, being how we manage the stack, how we manage the heap. The heap, if you recall, is the place in Scheme where all the con cells were stored. We'll talk a lot about that as the weeks go by. Okay, so that has to do with how we manage the memory. So let's go back now and actually start to do some of this stuff. In particular, let's ask ourselves, since we have a blank sheet of paper right now, what should instructions for this computer actually look like? Well, what do they need to do? A typical instruction, let me write this down here. No, actually, I won't even use the chalk this time. I'll just use the laser pointer, except it doesn't work. What do I need to do? There we go. Okay. So let's say that we wanted to add this big number to that big number and put the result in that big number. Well, what do I mean by adding the numbers? Do I mean adding the numbers themselves? Well, that's kind of a dumb thing to do. Let's see. What do I really want to do most of the time? Is this hard to see? Is it be better if I wrote on the board? Okay, let me write on the chalkboard.
I'm also colorblind and I can't see the...
Oh, you can't see the red. Well, then we won't use the pointer anymore. That's easy.
We can get a mechanical pointer.
Well, yeah, but I always hate those things anyway. I'll just use my hands. Okay. So a typical operation is we want to take X and we want to take Y and we want to add them to each other and we want to put the result into Z. Okay? And so let's say that we said set bang from Scheme here, Z to be X plus Y. That might be something we might want to do. And the question is, how do we translate this into an instruction for our computer to do? Well, in the Scheme register machine that you saw before, it was assign. Anybody want to help? Reg Z. Great. All right. Wonderful. Okay. And so you could kind of see how this instruction could correspond to one that this machine could do. But they never talked about exactly how you would encode this in bits. Okay? And they never talked about exactly where these data values were. That was all kind of left fuzzy. Okay? So let's say that we decided that the way we're actually going to encode it in bits is that we're going to have a field that corresponds to the operation over here. We're going to call that the opcode field, operation code. And one might say, for instance, that the opcode, and I'm just going to make this up, that the opcode 0 corresponds to plus, and the opcode 1 corresponds to minus, and so forth. Okay? One could just make this up. Make up a code for each of the operations you might want to do. Well, what else would we need? We need a place where the destination should go. And here you'll see that 6004, which is where some of this stuff comes from, and the beta in particular, was not created by people who programmed in Scheme, but rather by people who programmed in C. Okay? Because over here we would have some code to indicate the register Z. And that would be the destination of where the plus operation is going to put its value. And then over here, in these two other fields, we could indicate the two sources. That over here we'd have the register X, and over here we'd have the register Y. And so we would indicate in this instruction here, reading from left to right, that what I want to do is plus X and Y with the result in Z. Okay, it's just another way of coding this same thing. And I want to switch from this sort of scheme-like way of doing things to this way of doing things only because this is more typical of what's out there. And as soon as we ask ourselves the question, how does this work? I think it's better to answer the question as how does it usually work? Not how does it work in some weird system that's built at MIT, right? Okay. So it usually works that you have instructions in most machines that have these four fields: an opcode, a source, another source, and a place to put it. Okay, that's a typical thing. Now, we need to somehow figure out how do we encode the plus and the minus, which I just did here. We can just make up codes for them. But then how do I encode that I want this to go into the register X, this to go into the register Y, and this to go into the register Z? Well, I said before that we're going to have some big memory. And the memory is going to kind of have two things in it. It's going to have instructions, which are things that look like opcode, source 1, source 2, destination, and it's also going to have data. Yeah. And I draw this line, not necessarily, you may even mix these up, okay, but just to show that there's kind of two things in the memory, the main memory of the system. And the data will have things like, over here is the value of X, and that might be 17. And over here is the value of Y, and that might be 23. And over here is the value of Z, and that might be 40 after the operation. Okay? And so, in general, it makes sense to store the data and the instructions in this way. And now we're left with the question of how do we indicate where X is and where Y is and where Z is. Well, I talked about how we indicated where an instruction was because I said we would have something called a program counter. I'm going to abbreviate that PC for program counter. Does not mean politically correct. That's something different. And what that program counter is, and I'm going to draw a little diagram like this, is a offset. Let's say the memory starts at location 0 and then grows all the way down here to some large value. It's an indication of how far from the beginning that particular instruction is. So if this is 17 lines down here, the program counter would have the value 17 in it. Okay? And that, after it incremented to pick the next instruction, you'd find that right over here. In a similar way, this variable Z can be known by its distance from the beginning of the memory. And this distance here will be the address of the datum Z. And this distance here will be the address of the data X, and this will be the address of Y. Okay? So how far down we go in order to get the values. So in general, we are going to say that Z is located in a certain place in the memory. And when we say that, what we mean is that that's how far from the beginning of the memory one finds Z. Okay, good. Now, we're still not answering the question. How do I encode an instruction to talk about where X, Y, and Z are? Well, here's one way of doing it. In the three fields for the source, number 1, and the source number 2, and the destination, I can put in those offsets. What is the address of X of the first thing? What is the address of Y? And what's the address of the destination? So over here, let's say this distance over here from, no, I didn't draw this the right way corresponding to the picture, I think. But looks like X is in 4364. So this should be 4364. And again, what that means is that that's the distance from here to here. And Y was 932643. You can tell that I spent a lot of time coming up with these. I just typed like that. And Z is 43265. So clearly, this is what they call a non-monotonic scale here, right? Because this is lower than that is. So just imagine that we're sort of warped here a little bit, okay? But
The actual address in memory of where
that's absolutely right.
register is?
That's absolutely right. Except that sorry? Oh, what is the question? Good, I'm going to learn to do this here. Is that the address of where the register is? Now, I've sort of pulled a fast one on all of you. I've stopped using the word register. Instead, I'm saying that X, Y, and Z are variables that we want to do the adds on, okay? Because in general, when building a computer, there's no reason at the beginning to get fixated on this idea of registers. Instead, I'm saying X, Y, and Z are variables that live inside the memory of the system, okay? And the address of X, Y, and Z are these three numbers. And what an address means is what is the distance from 0 to where you find the thing. Okay? Good. Does that answer?
I think so, yeah.
Okay.
The registers just contain the addresses and they're pointing off the addresses or the location of the
Well, let's see. Yeah. So so what I'm trying to do is extract myself from this decision they did in the scheme book, which was that the contents of a register is always a pointer into the memory system, because what we're going to do is do something which is done more usually, which is to not do that and to allow the registers to have data in them too. Okay, so I'm kind of trying to pull a fast one, but you caught me. So let's not use the word register for the next 2 or 3 slides, and then we'll use it again, but in a different way. Okay, and hopefully you'll all forget the old stuff and think about it the new way. Because in real computers, the registers of the machine have all kinds of things in them, not only pointers into the heap, which is what the scheme book did. Okay, but for now, let's just think about, I have X, Y, and Z. They live in here, and here's the pointers to where they are. And one way of perhaps building an instruction set is to not have a register bank at all, but rather to have instructions that explicitly say the source is in this location, the other source is in that location, and the destination is in this third one here. Okay? Now, it turns out that, so here this is kind of a picture of what that looks like. So the program counter points into the program memory, this stuff up here, program memory, and the instruction has in its code pointers to X, Y, and Z. And I can point them on the left side or the right side. It doesn't matter. The number is the same, 4, 3, 2, 5. Okay. All right. The trouble with that is that if these numbers can get very, very big, if this is, 128 megabytes, let's say, or even bigger, okay, that's a very, very large number, 128 million. The number of bits you need to encode that, and hopefully you'll learn some of the stuff in the section. If not, we'll go to the next class, how you encode a number like this in bits, okay? Then it turns out that the number of binary digits you need in these fields can get very, very long. And so what you unfortunately end up with is a number of bits in each of these fields, which is very, very wide. And so for a typical way that you look in a memory system like this is to use 32 bits. So to go between the number 0, if I have a 32-bit string, right? I can go between all zeros. Let's say there's 32. Just pretend, okay? And all ones, right? And there's 32 of those. How many different combinations of zeros and ones can I have counting this? So it's 2 to the 32 different ones are in here, right? Which is approximately, even more. It's about 4 billion. It's about 4 times 10 to the 9th, okay? It's actually more than that, but, okay. And a good way to think about that is that 2 to the 10th is exactly, what? 1024, which is approximately 10 to the 3rd, right? So therefore 2 to the 30th is approximately 10 to the 9th, and 2 to the 32 is 2 to the 2 times 2 to the 32, so about 4 times 10 to the 9th. So this is 4 giga locations, right, between here and here. And that means this is a typical memory system that you see out there, 32 bits wide. There are some now that are actually 64 bits wide. That's even more. And unfortunately, if there are 32 locations, 2 to the 32 locations between here and here, it means that each of these fields needs to be 32 bits wide. And before long, when you add up this, if this is 32 and this is 32 and this is 32, you have 96 bits over here, which is a very wide word. The whole operation would be 96 bits for these 3 fields, plus however many you have for the operations you might want to do. And what I'm trying to say is that this is bad, because it's too wide. It's too wasteful of memory. And so we're not going to use this way of doing it. It turns out there's another problem with trying to encode things this way too. And this is a standard joke that I do in my class, and so you guys all get to hear this bad joke. Everybody wants a memory system that is fast and cheap, okay, and also big. Right? I want as many bytes as I can get for as little money as possible, and I want it to be incredibly fast so that the computer can run very, very fast as it fetches data from these different locations here and does reads and writes into and out of that memory. The problem is that a real memory system is either one of these things or the other. It's either the bunny, which is very, very small, and the cost per bit is very high, or it's this very slow memory system. As an example, okay, here is now this isn't quite true, but if you thought of this as a DVD versus a ROM, okay, this is a very big memory system, right? It has lots and lots of bits on it. If it was a DVD, it would have 5 gigabytes, roughly, 4.5. But it's slow to access, but it's very cheap, right? So you can kind of see that this is kind of more towards this end of the scale down here. Okay. On the other hand, the RAM chips that are in here, in the 64 megabytes or 128 meg, are much more towards up here. The cost per bit is much more high. Otherwise, I'd go ahead and get 5 gigabytes of RAM in that thing, which I don't do. And the reason is that it costs too much, right? But it's much faster to access than this thing. This thing turns around real slowly, and there's a laser beam, and all these things. Whereas with the RAM chip, it happens in a few billionths of a second and can randomly access the different points. And we'll get into all of this stuff, so don't worry if you don't happen to know that now. But this is sort of the trade-off that you have, okay? Now, it turns out that there are physical reasons why this is true. The more bits there are to access, the slower it is to get to them. If this class had 1 billion people in it, and I had to pick one person out, it would take longer for me to do than if there are the number that are here now. And the reason is that I first have to choose which row, then I have to choose how far down, then I have to find the person, and if there's so many of you out there, it's going to take me a long time to get to that person and back. So there are actually physical limits on how fast you can get to each bit. And in general, the larger a memory system is, the slower that it's going to be. It's also the case, from an engineering perspective, excuse me, that you can fit only so much memory on the integrated circuit of a computer chip. Okay, past that point, the chance of there being an error when you build the integrated circuit chip itself gets too large. And as you try to make these things, you find out that they all have some glitch in them, or that the number that have a glitch in them is too high and you cannot economically make them. So what that means is that past a certain size, the memory has to no longer be on the same computer chip as the arithmetic logic unit. It needs to be off chip, and the data needs to move back and forth. And as we'll see later on, it turns out that moving that data off the chip and moving it back onto the chip takes time. And thus another reason why the bigger the memory system is, the longer it takes to access it. Yeah?
If this isn't the right time,
No, that's fine.
But what's the physical basis for Moore's law and the increasing power of processors for the same cost?
With how things have been getting better with time. That has absolutely nothing to do with this. Okay, but you're absolutely right that Moore's law makes the boundary of what's on chip and off chip move all of the time, and it moves at a certain rate. As to why it happens to work that way, it's a fascinating thing. But we should talk about it, in some future. It's probably the last lecture when we're going to talk about that. So you couldn't have picked a more diametrical time. So you can all hang on to that question. Why is Moore's Law the way that it is? But the question is, and this is where everyone at MIT always cracks up, is can we do this? Can we somehow combine a small memory that's fast and a big memory that is slow and create a big memory that's fast? And the amazing thing, and don't try this at home because it won't work, in biology at least, is that it actually works inside of computers. And you all know that it works. And in fact, it works not only in computers, but in other things too. And a typical example is the bookshelf that you have at home and the library that you go to bring books in and out of and to replenish the books on your bookshelf. And so it exploits this particular thing that people do with books, and it turns out that computers do with memory systems as well, which is called locality. Okay? If you think about which books you read over a year, you do not randomly sample words out of all the books in the Library of Congress. That's not, you don't, wake up one day and say, okay, I'm going to look on page 354 of book number 1723 or something, and you go there and you read the word the, and then you put the book back and, you kind of leave, and then you come back the next day and you pick a different book. No, that's not true, right? You go there, you typically take out books on the same stuff, first of all, art or literature or skiing, God forbid, right? And you take out this book and you read things that are next to each other, even in the book, not only books that are next to each other on the shelf. So you tend to be local in what you access. In fact, if it's poetry, you tend to read the same things over and over again, because it's nice to read poems over and over again. And it turns out that computers do that too. Computers tend to access certain locations inside the memory that they have over and over again. And they also tend to access locations that are near each other. So let's think about how that could be. Here's a graph of what location. This is starting at 0 and going up to a big number. And here's time going by. And each dot here represents an access by the computer to a different location in the memory system. Okay? So what do you think this might be? Here it accesses this one, accesses something one more than that, one more than that, one more than that, one more than that, then goes back to accessing this one at the same time. What does that look like? The program counter, right? Going through a loop. It's accessing one instruction, the next one, just like the fact that we just saw, and going to the one at the start. So this looks like a loop. And then finally, the third time around, it gave up and then jumped up here and then goes down here. So you tend to see instruction accesses of instruction code that kind of have these lines in them, but they're very local. Okay? Okay, here's some data that looks kind of cool. So this is sort of squeezed here. So we're kind of going up and down and up and down and up and down. And then we go up and then down and then up again. What do you think would kind of move like a triangle wave up and down in a data area? And I briefly mentioned it. Wouldn't be sort of random registers or random variables like X, Y, and Z. Think about what we needed to do a recursive thing. We needed a stack, right? And the stack was something we pushed values onto and we popped values off. And they didn't actually talk about how the stack works in the Scheme textbook. So it's okay that many of you don't know this. But actually the way that a stack works is that you have something called a stack pointer, which we'll call SP. And the stack pointer points here. And every time you push something on the stack, you put a thing there and you increment the stack pointer. And then the next one goes here. And you increment the stack pointer. And now it's time to pop things off. You decrement the stack pointer. And you decrement it again when you pop off the next one. And so saves, which is what they called pushes. Okay, push and save is the same thing. When we put something on the stack, we save a value to the stack, would make the stack pointer increment. And restores, or pops, would make it decrement going back down. And so you would typically see an access pattern. This is a little bit strange here, but if you saw it kind of seesawing back and forth, that would be like a stack. And the locality that we have is broken up in general into two different things, like I just talked about. One is called spatial locality, and that says that if I refer to one word in the textbook, chances are I will also refer to the words that are near it in space. And the other one is temporal locality, which says if I access a particular word in a book, I will come back to it again with higher probability than other words. And so you can see examples of both of that here. Okay, so turns out you can make a big, fast memory by dividing your memory system up into two pieces. One is the big, slow one, which we'll call the main memory. I'll call this big, slow main memory. And then another one, which is much smaller, which I'll call the small, fast memory. We'll use this one as the bookshelf and this one as the Library of Congress. And what we'll do is that when we want to access a book, we'll go over here, we'll check out the data, the book, we'll bring it into here, and then because we're likely to use it again and again and again, we'll operate with it over here. And then when we're done working on it, and we get the little note in the mail saying that you're late, right? Then we'll bring it back here and put it back in here, okay? And by combining these two things, it will seem to us, because typically we'll be doing work here, as if we have access to the Library of Congress, but we only need to walk to our bookshelf to get to it. So it's fast, but it's big. Okay, we get the best of both worlds. And what we will call this small, fast memory system is the register file. And here's where I reintroduce the word register. But hopefully, it's no longer just a place with pointers into the main memory. It's a place where we shuttle data back and forth, the bookshelf to the library of the big, slow system. Okay? So inside of the processor, a great idea will be, instead of having these long words, remember the instructions had to be very wide in this case, we're actually going to make this memory incredibly small. It's going to start at location 0 and end at location 31. There will only be 32 places to put things. Okay? So, if I have 32 locations to put things, how many bits do I need to encode which one it is? 5 bits. Because 2 to the 5th equals 32. So 5 bits is enough. I put in a 5-bit number here. This is a way you write 5 bits. You have a line, slash through it, and the number 5. That means 5 wires that go in, 5 bits. That's enough to select any of the 32 slots that are here. And that means that our instruction word no longer needs 32 bits for each of these fields, but now can have just 5. And it's only 15 bits long. And these no longer point into here because they're forbidden from doing that, because they're not long enough to do that. But instead, they're going to point into different locations in the fast memory. You cannot hang out, well, this is not true in real life, of course, but let's say that you didn't like the place or something. You cannot hang out and read in the Library of Congress, but rather you can check out books and take them home and read them there. Okay? Here's your bookshelf. You can read and write this freely and do things like add and subtract and so forth. But if you want to have access to more, you need to transfer data between the big, slow system and the small, fast one with special instructions. We're going to talk about that next.
Now, each of those blocks, each of those 0 through 31 blocks, is actually the register that contains the data?
Mm-hmm. Absolutely right.
And do those have a width, maximum width?
So it turns out what we're going to do in this class, now modern machines are beginning to move from 32 to 64, both in how wide things are and also how long they might be. Okay? But for now, at least for the next 5 years or so, it will probably be stuck with 32. So that's how we're going to teach it now. But just keep in mind that there's nothing magical about the number 32, and as a result of Moore's law, it's going to grow pretty soon to 64. Yeah.
The beta register emulator, or whatever it's called, is comparable to the alpha.
It's very close to alpha.
At 64 bit.
That is right. And so it is a futuristic, we cut down to 32 because, in fact, in the MIT class, at least when I taught it, they used to build one of these things physically. And hooking up 64 wires is kind of tough. And even 32 is tough, and we had trouble doing that. But we needed to cut it down. So we made a 32-bit version of the alpha. So you're absolutely right. Yeah. But anyway, we're going to use a 32-bit wide system here. And again, you could change that pretty easily. Okay.
That just seems
Yeah.
so small, 32.
What's that?
It seems just so small.
It seems
I would have
small.
thought that would be bigger.
Well, let me think about that. Why is it that we don't use a longer word? In the old days, it was because memory cost a lot. It's not as true now. If you look at the Hennessy and Patterson book, I'm sure there is a discussion about where the trade-off is. In general, you have to ask yourself the question, how many different locations do I typically use in these opcodes? Yeah, Mike?
When you're pushing numbers around, remember that in the processor, you actually have to have wires that go from one side to the other one. So if you've got 32 bits, you need 32 wires to go everywhere. If you have 64 bits, you got to have 64 wires to go everywhere. And if you're only in 2D, pretty soon run out of space.
Except that it actually turns out that because of Moore's law, that number is not thought of as being quite so big anymore. So, right, and because things get smaller and smaller, and it's easier to build the wires than it was in the past. But there is another reason having to do with the efficiency of these opcodes. So let's say actually that these were 10 bits wide as opposed to 5 bits wide, or just making this thing a wider word, right? Having more registers. Because, of course, if this word is wider, then we can fit more stuff in there. The question is, are you using those bits well? And the answer is that there's an idea of how many registers your program tends to work with at any given time. And the answer is, past a size of 32 or 64 numbers of that order, it turns out that you don't work with more. The kind of code that we human beings write tends to work with a pretty small set of things at any given time in the code. So it really isn't necessary to have a register file that's longer than this, and as a consequence, it's not necessary to have a program word that's much longer than this. However, there are some specialized languages in graphics and so forth that are an exception to that. And those machines are called VLIW, for very long instruction word systems, okay? And again, the last day of the class we'll talk about, actually the second to the last day, we'll talk about VLIW. But for now, let's kind of put that off to the side.
There's also quite a lot of communication between the register file and
There is, but actually in the middle of the course, we're going to talk about putting something in the middle over here, in between these two things, okay, which is your local branch, okay? And that guy can send out a tag to the Library of Congress to ask for the huge book, but it's the branch that you take a 5-minute drive to get to, as opposed to the flight down to Washington, D.C. Okay, so we'll talk about that too, but you guys are very bright, so this is one of those kinds of lectures.
We sort of trash syllabuses, right?
That is fine. It's absolutely fine. So what kind of instructions do we have now that we have this small, fast system and a big, slow one? Well, we have instructions, instead of adding a pointer and another pointer, putting the result in the third pointer as we had before, now we're going to say things like add register 0 to register 1, putting the result in register 2. And this number that is at the end of the register will never get more than 31. It has a range from 0 to 31. We're also going to need some specialized instructions to do motion between the big slow system and the small fast one. And that's going to be called load and store. And load is going to be an instruction to bring something into the small memory. Keep in mind, again, it's a kind of calculator-centric view. So I load something in and I store something out, okay? And I store it out to the main memory and I load it in from the main memory into the register file. And so I'm loading from location 43264 into R0 and from this location 1. Then I would typically take this add statement and put it in the middle here. And then after I was all done, I would put R2, storing it into location 43265.
Does this mean we can't actually have 32 bits for our memory address?
Very, very smart, right. So now let's take a look at the encoding of an instruction to do load and store. Okay, we still need a few bits for the operation code, and we have remaining bits. This number here is not 32 bits wide, because this whole thing is 32 bits wide, so this must be less. And we're going to talk about how to deal with that in just a second. But it's at least longer than 5. Okay, so let's talk about that in just a second. Before we get to that question, let's talk a little bit about how I've kind of guided you into this 3 operand type of an instruction when it's not, doesn't necessarily have to be like this. And the reason, of course, we went this way is that the scheme book did it that way, and so we had an easy time choosing the same thing. But one might imagine not having one source, another source, and a destination in each one of these opcodes, but rather having fewer things and having some implicit way where some of the sources and some of the destinations came from. So one example, for instance, would be you would say plus R0, R1, and what that really means is take R0 and R1, add them together, and put the result back into R1. Okay? And these are called 2-address machines instead of 3, because notice here we have 3 different addresses of a register. And machines like the PDP-11, back in the days when I went to school, were like that. Okay? What's the advantage? The words are not as wide. Okay? And back then, every bit cost a lot of money. Okay? You could go even with less. 1 address. Add R0. What does that do? How could that work?
Another register that is fixed.
Absolutely right. So again, as with the case of the condition register in the scheme textbook, this implicitly talks about having a register off to the side called the accumulator. Okay? And what it would do is it would add R0 to the accumulator and put the result back into here. And so you got to choose what got added in, but the memory it got added into was always the same. And then you would again have instructions for pulling things in and out of here and putting them into the big memory. Okay? So the 68E11 is like that. And then finally there's 0-address machines like Java, the bytecode in Java, and actually a lot of codes in Lisp machines and stuff like that, which just say plus. Now, how the heck does that work? Anybody know? Java hackers? Well, it's a stack, right? And so here's the stack. And let's say that these two things, so there are many ways to draw stacks, okay? And I'm going to get used to this idea that this is the newest stuff on the stack down at the bottom, and this is the oldest stuff on the stack down at the top, or up at the top. And the reason that I'm going to draw it like this is that it's easier, because I'm used to writing one line after the other down a page, to put the newest stuff at the bottom, because that's how we think when we write, or that's what we're used to doing when we write. Unfortunately, this is opposite to our thinking that if I have a stack of dishes, where does the newest dish go? Most people don't add to a stack of dishes by putting one underneath, right? But we're going to think about the newest one down at the bottom here, okay? So the stack machine, you give an operation like plus, and it says pop the 2 things off the stack, and once they're gone, put the result back in the stack like that. So these 2 disappear, and then the result gets pushed on, like so. Okay? And so you see machines like this, and the operations that they have is push something from this location in the big memory onto the stack. Push something else onto the stack. Add. Pop off the stack back into a place here. Okay? And so the stack is acting like your small, fast memory, but you never get to choose where it goes. You only get to choose this place right here at the newest part of the stack. Okay? So anyway, there are choices there. There are also choices having to do with how complex the instructions are that go into this field right here. Whether you're going to do a plus or a minus, or you're going to say something like, take the fast Fourier transform, okay? Which would be a big deal, okay? Or a bigger deal. And there's a spectrum of how to do this. The simplest ones are called RISC machines. And RISC stands for Reduced Instruction Set Computer. And that means that the instruction set is very simple, and that's what the beta is like. And then there's the complex instruction set computer, and that's something like the Intel 8086, 486, Pentium, etc. And so the operations there tend to be more complex. And what the trade-off is here is how long it takes the computer to execute each instruction. And one would imagine it takes longer to do each instruction this way than it does to do it this way, versus how many instructions it takes to do the job that you're trying to do. And around 2/3 through the course, we're going to talk about this issue and why it is that we chose to do it like this. And more modern machines seem to be choosing this path than this path here. This tends to be the older type of way of doing things. So, and the Hennessy and Patterson book does talk about that very well too. Okay, the rest of this lecture is going to be sort of grungy. We're just going to actually talk about how the beta is built. And some of this you'll see is kind of very close to what I've written here, and then there'll be some newer stuff. But you're not going to get it from just listening to me, okay? Because it's just going to be tons of stuff. And don't bother to write it down. Everything that you see here is going to be in handouts, the references that you're going to see. And furthermore, when I'm done and you take a little break, Mike is going to talk a little bit, and he's going to show you how to use the simulator. And of course, it's by using that system that you're going to learn for yourselves what all these rules are. But I want to talk about what the rules are anyway. So we talked about there being a program counter. That's this storage right here. And that's going to point into the memory system. And it will always point to where the next instruction is that we're going to do. So the PC is a value. Itself is 32 bits wide. And it's going to point to where we get the next opcode was from. And the loop of fetching an operation or an instruction and executing it works like this. Fetch, and I'm going to talk about this a little more in a second, the contents of, these little brackets are the contents of the program counter. So the PC is this thing. The contents of the PC is this pointer. Then take the contents of the program counter, increment it, and put the result back into the PC. So before we execute the instruction, we're going to find out what this is, store it on the side, and we're going to increment the program counter. Then we're going to execute the instruction counter that the program counter pointed to, and then we're going to do it all over again. So each time we just get the next one, 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 going down the instruction memory. Now, this is 32 bits wide. We say that it's 4 bytes wide simply because of the notation that's become common that 8 bits is 1 byte. Okay, BYTE is 8 bits. So 4 bytes is 32 bits. We're going to do something a little bit funny. It turns out that having the constant 0 is a handy thing to have. First of all, if you want to test against the constant 0, as we did in fact, it's nice to have a 0 to test against. Second, if you want to do things like starting a loop at 0, that's also very nice to have too. So we're going to actually say that we're going to throw away one of the registers, and we're going to make it always 0. If I read register 31, the last one of these 32 registers, it will always be 0. What happens if I write it? Smoke comes out of the system, right? Conflict between zeros and ones, and no, it just throws out the bits. Okay, so register 31 is a handy. I don't know if you guys have ever heard of this dev null. You know, the Linux hackers, right? You write it, it goes away. You read it, it's 0. It's what's called a bit bucket. Okay, just throw out the bits, and it will actually be the case that some of the time we're going to do an operation where we throw away the answer, and you'll see why we do that. And there's no better place to throw it out than register 31. And sometimes we'll just want a place to get a 0 from, and we get that from the same place too. So that's some of the quirks here. And again, you don't need to know this now, but just to get you an idea. I introduced this idea of the contents of the PC. Let's talk about the language that we're going to use for talking about how these operations work, because we're going to be fairly formal in how we do it. The general idea is that this arrow, less than dash, is indicating that data moves from a particular place to a particular destination, except that the two sides of the arrow are not symmetric. Now, I hated this when I first took this course, and I learned about this, and I've always tried to figure out some way to build a system where this isn't true, and I could do it, okay, but then it would be just like the scheme textbook, because the rest of the world does it this way, okay? So we're going to teach it to you the way the rest of the world does. On the right of the arrow sign is a value, like the number 3. On the left of the arrow sign is a location where the 3 should go, okay? If I have a location on both sides, I have to do something special saying, I want you to fetch me what is in the location and then put it in a particular other place, okay? So surrounding something with angle brackets like this says use the thing inside the angle brackets as a pointer and find out what is in the location that that pointer points to. For those of you that know C, this is just like star, okay? Do a reference through the pointer. So for instance, 56, angle brackets. What is in location 56? find out what's there, and put the result into location 34. Now, if I think about that, inside of here, here's location 34, and here's location 56. I'm taking data from here, I'm moving it into a place here. That's what that just says there. Now, you would think that the left and the right-hand side, talking about where it comes from and where it goes, would look the same with the 34 and the 56, but they don't. There's one more indirection on the right-hand side than there is on the left, because it's assumed that the arrow means on the right is data, on the left is a place. Okay?
Is this a description, or this is actually literally characters typed into this system?
This is a formal mathematical notation for how to describe the movement of data in any system. And it's actually called register transfer language, and it is used throughout the computer design business to talk about how data moves from one place to the other. For the Pentium, for example, there's a thick book that is basically filled with stuff like this.
This is not an actual assembly language?
No. This is just a sort of a way that we talk about it in a formal sense. So what does this mean? 56 goes into 34. Well, you have to think about it. It means the constant number 56 goes into location 34. So that would mean find location 34, doesn't matter what's in here, and put the number 56 inside of there. Okay? Where 34 is the pointer, and 56 is the data. Okay? And 56 going into the contents of 34, this is the hard one, because you think that this means what I just did, but it isn't. This contents of 34 is a location, and the 56 is the data. So what that says is that if, now let's get rid of all this stuff, if this happens to have a 17 in it, it says on the left-hand side, find what 34 points to, and that will be a location number 17, into which I will write the value 56. Okay, that's what the last thing means. Again, don't worry if you don't get it now, but you'll have practice doing this all of the time. Let's actually talk about the encoding of the instructions in the 32 bits right here, the way that we do it. In general, we have 32 bits to deal with, and here's how we're going to do it. We're going to use 2, 4, 6 bits to specify what operation I want to do. Plus, minus, times, things like that. 6 bits, how many different opcodes can I have?
64.
2 to the 6 is 64. Good. Register A will be here. Then we're not going to use a bunch of space because we don't need it. Register B will be here, and register C will be here. And again, the encoding will be left to right because, at least here, that's how we read. And so register A will be a source, register B will be a source in general, and register C will be the destination. So if this is plus, and this is a 0, and this is a 1, and this is a 2, and this will say take register 0 and register 1, add them together, and put the result into register 2. Each of this is 5 bits wide, so it can specify one of 32 registers, which is in our register file. That's one type of instruction that we're going to have. The other type of instruction is going to look like this. An opcode, one register, a constant, and another register. And so we will be able to say things like, take register 0 and add 56 to it by putting the number 56 in the bits here, and add those two things to each other and putting the result into what's indicated by register C. And it turns out that it's often handy to be able to specify constants inside of the instruction field in this way. And so that's why we have an alternate way of specifying the different things. And to get to the question that was asked before, loads and stores are going to have to make do with 16-bit constants, which is going to make storing into a location that's way out here past 16 bits hard to do, right? Because what is 2 to the 16? See, if you learn nothing else, you're actually going to know what all the powers of 2 are. 2 to the 16 is 64K, right? Which is actually 65535. 2 to the 16 equals 65536, actually. Right? It can't be an odd number, hopefully. Which is equal to what they call in our lingo 64K, where a K is 1024 in decimal, okay, in units.
I'm wondering, is the assignment or the storing, is that implicit in the operation code?
Yes.
Or in the instruction set? Because when we did it here with our, what was that, RML, we had the assign and we told it explicitly to assign.
That's absolutely right. There will be special opcodes, load and store, which will do what we want to do. Otherwise, what the opcodes will do is always store into what register C tells us what place we want to store. So you'll actually see that as we go through, okay? So those are the two forms that we have. But we want to think in our heads, how are we going to get past trying to load and store between, here's location 0, here's 65535. This is actually 65536 different places. How are we going to get to read and write out here? And you'll get to see how, okay? But so far, we only have 16 bits of constant in there. Okay, as I said before, everything is going to go from left to right, and that's going to make it very easy to understand how things go. So add of RA to RB, putting the result in RC. Again, in the register transfer notation here, the contents of RA is added to the contents of RB, and the result is put into the location specified by RC, where each of these RA, RB, and RC are numbers between 0 and 31, and they all mean places in that register file, and of course R31 is read as 0 and can be written and nothing happens. Okay, and that's form 1. Form 2 is going to be, I want to take the contents of RA and add it to a constant, and we're actually going to use what's called the sign extension of a constant, and all this means, and we're going to talk about this either in the section this afternoon or in the next class, that you can specify both positive and negative numbers inside of here. And for now, that's good enough, and let's not talk about it more. But in any case, we add the constant to the contents of RA and put the result in RC. And the way that we differentiate between which form of the two opcodes we're going to use is that we actually use a different opcode for it. These 6 bits here will have one combination that means add, and another combination that says add constant. Okay? The plain add will be to add 2 registers, putting the result in a third. Add constant means add a register to a constant, putting the result in the third register. What's nice about this is that RA is always in the same place, RC is always in the same place, and the only issue is it the contents of RB or the constant that's specified as part of the instruction itself. There will be different operations. There will be add, subtract, multiply, and divide. The logic that will have things like AND, OR, and XOR, and associated with each one of the ones that operates on 2 registers, putting the result in a third, will be ones that operate on a register and a constant, putting the result into a register. There will also be shifts. I don't know if you guys have done in math bit shifts. If you shift a word to the left, it's like you multiply it by 2, right? Shift it to the right, it's sort of like dividing it by 2, except if it's negative and then it rounds the wrong way. Did you guys do that or not? Yeah? Well, okay, so we'll get into all of that too.
If you have subtract, why do you have to have a negative constant?
That's a great question. Let's see, what's the answer? I actually don't know the answer to that, so let me think that over. But I'm trained to always say that's a great question. Okay. Let's see here. And the next question is, how to get to the next slide. Okay, so we got the operate instructions, and now we're going to have the instructions to move between the small, fast memory and the big, slow ones. And those are called load and store. And here we're going to see how to get around the limit of 16 bits. Because it turns out that the address in the big memory that we're going to load and store from and to is not just the 16 bits that we specify in there. Remember, all of the operations have 3 variables. Sometimes there's a constant in the middle, but there's still 2 more. So load is going to say take the constant, add it to the contents of a register you get to specify. This register A, any number between register 0 and register 31. Add the constant, which may be negative, to the contents of the register, and use that addition, the result of that addition, as a pointer into the big memory. So all I need to do if I want to access a large place in the memory past the 64K boundary, somewhere way out here, is arrange for some register here to have a number in it. And remember, these are 32 bits wide, right? That points to somewhere near there, where near means within 64K of there. And then I can add a constant of between 0 and 65536, or it's actually between plus and minus 32K is really what it is, to that number that's giving a pointer to. And since this is 32 bits wide, I have access to the whole memory. And that's how we get around the 64K boundary. Now what's really nice about this is that you'll find that it's tremendously useful if I have an array of data, for instance. Let's say I have, put it up on the board here, an array, x sub 0 through x sub 49. What I would typically do is I would arrange for the constant to point to x sub 0. And then the register would tell me how far into the array I want to go. So the index would be in a register, and the constant would point to the very start. That only works if we're within the first 64K, but it still does work, okay? And I can encode how to access a particular place in an array within an operating system. I'm adding together these two things, which is what I have to do if I want to access an element of an array of data. Okay? The other thing that I might want to do is I might want to have a structure in here, like a record for a person that has their age and their weight, okay? And another structure for another person that has their age and their weight. And I might put in the register a pointer to which of the structures I'm going to access. And then the constant would be how far into the structure I want to go. So if I wanted to get the age, the constant would be 0. And the pointer would point to which of these things, the register would point to which of these ones I want to do. If I wanted their weight, the constant would be 1. And then whenever I used the same pointer to the beginning of the structure in the register, adding 1 to it would give me the weight part of that structure. So adding together numbers in references to the big, slow memory is a good thing to do. And that's exactly what we do for load and for store. Notice how store works. Store takes the contents of register C and puts the result in contents of register A plus the sign extended plus or minus 32K version of the constant. Again, the same idea of what is going on there. Okay, I want to talk about this just a little bit. A lot of computers allow you to read and write parts of the main memory system that are aligned with a byte. So remember, a 32-bit word like this, the words in this case are one slot here, have 4 bytes in them, each of which is 8 bits wide. And most computers these days will allow you to individually read and write pieces of this thing, saying, I want to have a pointer into this part right here. Okay? And it leads to a difficulty in learning this stuff because even though the pointers to here go up by 1, the pointers over here go up by 4. Right? So if this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, it becomes very hard to keep track of what it means to go to the next word. Do I increment by 4? Do I go up by 1? What is it that I do? To simplify this in the beta, we have done something which is actually used in kinds of processors called digital signal processors, which is that we've said that all of the accesses will be 32 bits wide, period. Okay? And so if this is location 0, the next location is location 1. And each location is 32 bits long. Now, most computers that you will use on your desktop don't work like that. Every 32 bits goes up by 4 because each number accesses a different byte of the 32 bits. But to just make it easier here, we just said this is a word-based system. Every word is 32 bits wide, and every pointer points to the next one. You just bump up by 1. And so I just wanted you to all know that for those of you that are used to pointers on things like the Pentium. Let's go over this kind of quickly because this is, again, a topic we're going to do in the next class, but just to show you how branches and jumps are done, ifs and go-tos. Well, remember that there was this condition register in the scheme register machine code. Well, We don't do that here because, in fact, that's kind of an old-style way of doing things, and it's a little gross because you never know where the result of a test is going to go. So what we do instead is we get to specify which register gets tested. In particular, I can have an instruction like this saying branch 0, register A, a label, and register C. And what that instruction does is it fetches the contents of register A, looks it up, 32 places there, tests if it is 0. If the contents of the register are 0, then we branch by adding a displacement to the PC, and the displacement is equal to register C plus the label. Okay, no, I'm sorry, that is wrong. The displacement is equal to the label. And we'll talk about the use of register C later, okay? I said a very wrong thing, okay? There's a constant here in the middle. Remember, the middle part is a constant that tells us how much to add, plus or minus, from the PC in order to branch. Similarly, there's an instruction called branch if not 0, which will test a register, and if it is not equal to 0, it will add the constant to the PC. Okay, so that's the way that we do ifs. And that means that you can use any one of the 31 non-zero registers that are out there as the condition register. Okay? I can test whether something is equal to 0 by putting it in a register and just using that register as my branch register, as the register A in the branch. How do I do an unconditional branch? Which register should I use? I will give you a hint. That one's 0. So if I do branch if 0 and use register 31, does it always branch? Yes, it always branches. Okay, so that's an easy way to do it. And so that's exactly right here on the board. So if you're reading ahead, you get it?
So we can only jump by 5K, right?
By
Or,
32K, plus or minus 32K. That's absolutely right. Except that sometimes you have to branch further. And in fact, sometimes you want to branch to a location that you don't know how far you want to go. An example, and you've seen this in Scheme, is a dispatch table where, depending on the contents of a variable, how far you want to jump is dependent on what that variable value is. And so we provide another instruction called jump, which is different than branch. And this is actually a common nomenclature, even though you would think that branch and jump mean the same thing. But branch, think of little branches on a tree. Branch is short distances, okay? Typically used in loops. Hop a short distance back, hop a short distance forward. Jump is like, the long jump, okay? And furthermore, jump, you get to choose where you go to in a much more sophisticated way. Here, we're branching a constant distance from where we are now. And again, we'll talk about the use of register C later. I'll give you a hint. It is exactly the same as the continue register in Scheme. In other words, this will be where we store where we came from. But we'll talk about that later in the next lecture. With jump, you get to say, I want to go to the contents of register A. So I get to specify a register between 0 and 31, and whatever value is in here is read and put into the program counter, and the next instruction comes from there. So I get to jump anywhere in this whole thing. All I need to do is arrange to get the value loaded into one of the registers here, and I just say jump to the contents of this thing. Okay?
Doesn't that still have the limitation of it's only 32 bits wide?
Well, 32 bits wide is okay, because memory is only 32 bits long.
Oh.
Okay. So, and at least for now, that's good enough. Okay, so our programs are not longer than 4 gigabytes. I know that Bill Gates will hate that, but Yeah.
The real world example where you were saying you pointed to the bytes.
Yes.
inside
Yeah.
those,
Yeah.
Does that mean that there's 4 times 32 bits worth of addresses?
No, well, we aren't going to use the byte thing at all. So in the real world, it would be, what you actually do is typically, so here's how bad it is, okay? Typically, if you're accessing the memory as data, you can get to the bytes. But if you're jumping to a particular place, you're forced to assume the last 2 bits of that place are both 0, so you have to go on a word boundary, or else the thing blows up, okay? You get an error. And so rather than deal with that whole mess, we're just forcing everything to be on a 32-bit wide boundary.
Theoretically, because we're only using words, we could actually have a 16 gigabyte main memory.
16 gigabyte, yes. Yeah, so this is 4 gigawords long, which is 16 gigabytes. So if I said gigabytes when I meant gigawords, that's wrong. Okay, very quickly, because we're probably over time here, let me talk very briefly about the kind of styles that we're going to use. And again, you'll be used to this because I've said it before. Variables in general will live in the big memory. X and Y in the big memory. This is how we're going to draw it. The ALU, which is the arithmetic logic unit, will operate on the registers in that small register file. Both the variables, excuse me, I said this wrong here, the variables and the instructions will both live in the big memory. And so therefore, what the registers are holding are temporary values, which we have fetched from the main memory into the register system. We've operated on them and then put them back. And so a typical thing of saying we're going to set Y to X times 37 would be translated into, let us load location 1002, the contents of that, into R0. Now remember, how does load work? It adds a constant to the contents of a register. The handiness of having R31 be 0 all the time. What I want to really do is I want to fetch the contents of location 1002, because that's where X lives. Oh, I can specify the number 1002 as part of this opcode here, but I need to add 0 to it. And so since this forces me to add the contents of a register to the constant, I just use register 31 as the register to add the contents of to 1002. And I load what's in location 1002 into R0. Then I multiply the constant, 37 times R0, and I put it back into R0. So I'm doing kind of a one operand type of thing where I'm just saying, use R0 as a scratch space. Then finally I store R0 into the location 1003, again summed with the contents of R31. And again, we especially set these things up so that everything always goes left to right. The data always flows from left to right. And so the way you think about it here is that these two things are added together to specify the address to read the data from in the big slow memory. The results are written into here, left to right. This is where the data comes from, and the result goes into the sum of these two things in the big slow memory. It's always true that the memory is accessed by summing two things. In this case, the constant R31. In this case, this constant R31. And here's where the register file is spec'd. Okay, so again, we move things from big to small, do work, and then put it back. We also, it turns out, in the assembler that we have all kinds of ways to write this so that you don't have to put all these bits in here. And what you do is you say the variable X is in location 1002, the variable Y is in location 1003, load X into R0, multiply R0 by 37, putting the result into R0, store R0 in the Y. And it turns out that our assembler is going to be smart enough when it sees store of one thing into the other, it's going to say, what they really wanted to do was to add 0 to Y and store R0 into that place. And it'll expand this into that. And so you'll be able to type in code that's really easy. And you won't have to be always doing this thing with R31 and stuff like that. And doing this will teach you how to do it. Okay? Me talking about it now will just seem like a big mess. So, let's talk about this just for a few seconds. Constants. If I have a constant that is small, that is less than 16 bits wide, in other words, in the range of negative 32K to positive 32K, I can put that into an instruction. So, for example, I can put the number 3 in here. Okay? But if I have a constant that is bigger than that, and I want to use it, what do? The answer is, I can put it in the instruction stream itself. I can have, X over here, I can have Y over here, and a constant C here, and I can put up to 32 bits worth of data inside of here. And as long as I can arrange to get a pointer to a piece of data that is wide like this, I can use a number which is more than positive or negative 32K. So the way that we get around the limit of how long a constant can be is whenever we have a constant that's bigger than 16 bits, we give it a word in the data section of the big slow memory, and then we just get a pointer to it and we get it from there. Okay? So as an example, here we load C into R3, and that puts this big constant into R3, and then we can now use it in our code down here. Okay? Again, I'm going through this very, very fast, I know, and I know that most of you are not going to get most of it, but that's okay. Very, very quickly, because you're all going to get to do it, okay? So, and you'll learn it like that. But I want to show it to you first. How would we do fact iter now, which we saw before in the beta assembly language, or in the beta instruction set architecture? Well, we have a variable n that is 20, a variable val that is 1, and those are in the big memory, those big variables. What do we want to do? Well, we want to check if n is equal to 0. So we load n into R1, and this expands into load the location here as a constant, plus the contents of R31, which is 0. Use that as a pointer into the memory, look up what's in there, which is going to be this 20 here, and put that into R1. So we're moving things from the main memory into the register file into register 1. Compare if equal register 31, which is up 0. Compare if R1 is equal to 0. And put the result of the comparison into R2. The result will be either 0 or 1. 1 is true, 0 is false. Now, some of you will yell at me and say, you don't need to do this. And we'll talk about that in just a second. But we're trying to check if R1 is equal to 0. If the comparison results in a true, then the comparison will be 1. In other words, R2 will get the value 1 in it, saying it is true that R31 is equal, that R1 is equal to 0. So if this is not 0, in other words, if this is true, then branch to done, which branches down here. This is really dumb code, okay? And we'll talk about how to make it better. But again, we're just being very dumb. We're just saying, I want to load n, I want to compare it to zip, and if the comparison is true, which is what this says, then I want to branch down to here. You can also actually say branch true. Okay, this is a kind of a dumb way to do it. Okay, if it's not equal to 0, then what do I want to do? Well, first I want to load val into R3. I want to multiply R1 times R3. Now, what is R1? That's n, because I loaded that up here. I want to multiply R1 times R3, put the result in R3, again, left to right. Then I want to store R3 back into val, because that's where what we're trying to do here. You know, val gets val times n. And then I want to subtract 1 from R1, because R1 is n. And then I want to store the result back into n. So now val and n have been updated with val times n and n minus 1. And then I want to branch unconditionally back to the loop here. And that's what the code looks like. Again, you're not going to get it now, but as you write it, you will get it. We can be better than this, and we can optimize this a little bit. So let's take a look at this. Load n into R1, load val into R3, compare if R1 is equal to zip, put the result in R2, branch if that's true to done, that's the same as before. Multiply R1 times R3, put the result in R3, subtract 1 from R1. But now we branch back to loop. And look at what we've done. We're only getting the big books from the big library once. And then we're operating on our bookshelf many times. And then when we're done, we're going back and putting the results back into the big slow memory. And so this moves the loads and stores out of the loop, which is, again, a typical thing that is done in a compiler that's translating, for instance, from Scheme and Beta, because those take time, and why bother to travel back there over and over again. And this is exploiting the locality here, right? Our loop is dealing with the same n and val all of the time, so let's not keep walking back and forth. Let's just do the work here and then go back once. Another thing that we can do, real hacking, okay? Well, first of all, we're going to forget about this dumb test to compare R1 to 0, because branch already sees whether or not a value is 0. So we're going to put n in R1, val in R3, branch if R1 is 0 to done. Otherwise, multiply R1 by R3, subtract 1 from R1, and now branch if R1 is not 0, back to loop. Notice that the one if test has actually split up into two opcodes. One at the beginning to make sure whether we should do this at all, because of course it's possible that n is 0. Right from the bat, you shouldn't do it at all. And that's what this is testing for. And then if n is not 0, we go into this loop, and we use this as the very last thing we do, and we just go around and around and around and around. And then when we're all done, we go back to the Library of Congress and we store the values. Okay? So we've reduced fact to 3 opcodes, which can run very, very fast. And you're going to get to do all this kind of stuff on the problem set. I'm actually going to skip the rest of this thing because I think that it's too much, and you get to see it in the problem set. It's not that big of a deal, but it basically talks about the tools that you're going to use that are going to translate the text that you type, like branch R1 da da da, into a set of bits, which are going to go into the memory here, which is going to encode these opcodes of 6, 5, 5, and 5. Okay. All righty. Questions?